Hello friends, welcome once again to my channel Pankaj Lade, your one-stop solution for maths, mechanics and drawing. In our previous lectures, we have seen basic definitions of integration and we have seen a long list of formulas of integration which were derived from derivatives. In our today's session, we are going to learn one very important method of integration which is called integration by substitution. And using this theorem, we will also be looking at some corollaries which are based on these theorem. Now, this theorem is going to be also asked in the exam many of the times, usually for 3 to 4 marks. So, it becomes an important concept with respect to the board exams as well. So, let's begin with what the theorem actually is. First of all, let us start understand what the statement is given to us. If you observe, the statement given to us is, if x is equal to phi of t is a differentiable function of t. Now understand the first line. He is telling that x, some variable x, is a function of t, some other variable t. So you have x as a function of t. So that function I have represented as x equal to phi of t. Not only x is a function of t, it is also a differentiable function. That means if you try to get the derivative of x with respect to t, that means dx upon dt, there will be some answer. So when I say x equal to phi of t is a differentiable function of t, it simply means x can be differentiated with respect to t, you get dx by dt is equal to some answer. So that is what the first line of the statement is conveying this. Then he is asking, if this happens, if x is a function of t and a differentiable function, then you show that integration of some other function f of x. Now f of x is a different function. It is a function of variable x. So integration of f of x, but as you know, x is a function of what? T. So integration of f of x, x contains t, the answer comes integration of f of phi of t, phi 1 of t, where phi 1 of t is the first derivative of phi of t, and dt. Now at the beginning, the statement looks very confusing. What the statement is trying to actually tell us, we are not able to know. Let's not worry about the statement at this moment. As and when the proof goes on, we will come to know what basically the statement is going to tell us. So if I use a substitution x as phi of t, that means the variable x is changing to some other variable t, something should happen to dx also, because your original variable integration of f of x dx variable is x. You are telling that now the variable x I am going to substitute as t, so dx should also change, and what that change is phi 1 of t dt. So that is what the theorem is basically trying to tell us. If I do some kind of a substitution for x, there will be something happening to dx, and what that something is this phi 1 of t dt. So whenever I say phi 1 of t, I simply mean first derivative of phi of t. Let's begin the theorem then. What things are provided to us? He is telling x is equal to phi of t. He is asking integration of f of x dx. Let us say that integration of f of x dx. People, if I get integration, there will be some answer. Say integration of sin x, you must be remembering it is minus of cos x. Integration of sec square x, you might be recalling it is tan x. That means whenever I have a function and if I integrate it, some sort of answer is definitely going to come. That means integration of f of x dx, there will be some answer. Let that some answer is g of x. Now I am not purposely putting c over here because we already know we are doing indefinite integration, and whenever we are doing indefinite integration, a constant is going to come. So let's not complicate the things very much by writing plus c over there. So plus c is there, we are not just writing it. So integration of f of x dx is, let us say, g of x. I will call this as first equation. We all know that integration is antiderivative. That means when the derivative goes on the right hand side, it is going to become integration. Exactly in the same way, when the integration goes on its previous side, it will again transform back into derivative. So when the integration goes on its original side, it is going to become derivative. So this integral sign, when it goes on the other hand side, becomes derivative. Integration is carried out with respect to dx. So derivative will also be done with respect to dx, that is x, the variable. So therefore I can say by definition, I'm going to send this integral sign along with the dx on the right hand side. So what is left on the left hand side? It is f of x is equal to integration goes on the other hand side, becomes derivative. Derivative done with respect to x, so d by dx of g of x. Now when I say d by dx, it simply means first order derivative of g of x. So the first order derivative, I will write g1 of x. The first order derivative of g of x, g1 of x. I am going to call this equation as second equation. So I had integration of f of x. I have taken the answer as g of x. What I have simply done is I have sent the integration dx on the other hand side. It has become derivative. It is a first order derivative, so I will write it as g1 of x. Those are my first and the second equation. What do you know about x? X is a differentiable function of t. The statement is already telling us that x is a differentiable function of t. I am writing it down. Since x is a differentiable function, it's a differentiable function of t, that is, he is telling me this x equal to phi of t. Can I differentiate both sides, let us say, with respect to t? I will differentiate both sides with respect to t. You must be recalling, if I have y is equal to f of x. This is what we have seen in derivatives. When y is equal to f of x, then if I differentiate both sides with respect to x, I get dy by dx is equal to first derivative of f of x, f1 of x. So dy by dx came f1 of x because y was a function of x. Here x is a function of what? T. X is a function of t, hence we will differentiate both sides with respect to t. So differentiate both sides with respect to t. So what are we getting? Therefore, I get dx by dt. This is first order derivative, so I am going to write phi1 of t. So dx by dt is phi1 of t. Let's move ahead now. I am going to call this as equation number 3. Let's move ahead now. Now people, this step is the most important step of your proof. Make sure that you note down this step as an important step, because without this step, the proof is not going to proceed further. You will not be getting your answer. So make sure that you halt at this place and note down this step as an important step. Observe here. Do you know that x is a function of t? Now if I ask you to differentiate g of x with respect to t, that's the key step of the theorem. What did I do here? I am differentiating g of x with respect to t and not with respect to x. That's a very important step you need to take care of, because we know that x is a function of t. That means g ultimately depends on t. G is a function of x, x is a function of t, so g ultimately is a function of t. That means I can say g is a function of x, x is a function of t. That means I can say g can be differentiated directly with respect to t through x. Through x. Do you know that this is called as chain rule in derivative? So I am differentiating g of x with respect to t. Look at my derivative. It is going to be derivative of g with respect to x and derivative of x with respect to t. That is what the meaning of chain rule is. So I will write my chain rule from looking at a diagram. So I will write here derivative with respect to x, d by dx, because the intermediate variable was x. So derivative of g with respect to x. Derivative of g with respect to x. And g is nothing but g of x. So derivative of g with respect to x into derivative of x with respect to t. So I write dx upon dt. Isn't it simple? So derivative of g with respect to x and again dx upon dt. Now you must have already recognized that I am trying to find derivative, first derivative here of g of x. The first derivative is denoted by g1 of x into dx by dt. Isn't it? So g1 of x dx by dt. Look at all the equations very carefully. See, g1 of x is here. G1 of x, if you observe, it is f of x from equation 2. So G1 of x can now be written as f of x. I write f of x and dx by dt. So this I have brought from which equation? Equation number 2. So I am right from equation 2. So d by dt of g of x. Until now I have reached up to f of x dx upon dt. Now I am going to change the variable. I am going to write x. What is x if you know? X is a differentiable function of t. So x is phi of t. So I am going to change my variable from x to t. So further I can go ahead and write d by dt of g of x. I have got my answer as f of x and dx by dt. But now I know I'm going to change my variable x to t. X is given to me as phi of t. So f of x is given to me as phi of t. So I replace x with phi of t. And then dx upon dt. Did you notice dx upon dt is already obtained somewhere in the entire proof? If you observe all the equations here, see dx upon dt is obtained in equation number 3. So I'm going to get dx upon dt from equation 3 and answer was phi 1 of t. So I get dx upon dt is phi 1 of t. So which two equations I've made use of here? One of them is x is replaced with phi of t. So x is replaced with phi of t, which is here. And the other equation that I've made use is dx upon dt is phi 1 of t, which is numbered as equation 3. So I'm going to write from equation 3. So far everyone has understood, isn't it? Now, do you also remember that the d by dt, when it is sent on the other hand side, is going to become what? By basic definition of integration. It will become integration. So I'm going to say by definition of integration, the d by dt, the derivative on the left hand side is sent on the right hand side, so it will become integration. So when d by dt leaves the left hand side, what is left on the left hand side? Only g of x. The d by dt, the derivative, went on the right hand side. So I write integration of what? F of phi of t into phi 1 of t. Now since integration is always accompanied with a variable, it was d by dt on the left. So integration with respect to t. So I write dt here. And if you remember, somewhere previously we have also written some expression for g of x. Look at equation 1, g of x. Equation 1 contains g of x. So g of x is nothing but integration of f of x. So this g of x, I am going to write integration of f of x dx. So I write here integration of f of x dx is equal to integration of f of phi of t, phi 1 of t dt. If you observe my last statement, is it exactly same as what he's asking? Integration of f of x dx is equal to integration of f phi of t, phi 1 of t dt. So that's how this statement, this proof is done. I want you to write this proof at least 3 times to understand the flow of the proof, to understand the most important step that I've already told while discussing this proof, so that this entire proof you remember it very thoroughly in your exams. So that's how the theorem goes. We will definitely be looking at some of the corollaries which are based on this theorem in our next lectures. Thank you so much for watching. Have a great day.